In 1610, Galileo looked through a telescope as he explored the cosmos. Saturn stood out amongst everything. He thought these were a set of angles on a planet, and Galileo recorded all that he saw, drawing these strange angles onto the side of Saturn. He couldn't figure out what these were, but in 1655, Dutch scientist Christian Huygens improved the telescope and made the discovery that Saturn had a thin, flat ring system. This started a huge debate amongst the scientific community. Just think about it. An idea that there is a ringed planet seemed stupid, so there was a lot of skepticism. But technological advancements in telescopes continued, and observations made it clear that Saturn did have rings, but these rings were way too complicated and complex, and we couldn't figure out what they were.
17th century stuff.
This problem took up most of James Clerk Maxwell's time, even though he was known for not concentrating on one research topic at a time. This was different. How could such a strange structure be stable? Why did these rings not break up, crash down into Saturn, or drift off into space? This problem has been puzzling astronomers for 200 years, but now St. John's College, Cambridge gave it a special attention by choosing it for the prestigious Adams Prize. This was created to celebrate John Couch Adams, who discovered Neptune, but this was to make up for when for 4 years Adams has spent doing manual calculations to predict the position of this new planet from these small wobbles in the movement of Uranus. But when he presented his prediction, it was ignored by, at the time, astronomer royal Sir George Airy.
The following year, the Frenchman Eben Leverrier independently made a similar prediction, and his wasn't ignored when he sent it to the Berlin Observatory.
And they immediately trained their telescope to the spot and found the planet.
So Airy made the claim on behalf of Adams to kiss and make up, and at the end, Adams and Leverrier got equal credit, and Adams later on in life himself became astronomer royal.
But back to James Clerk Maxwell.
So the Saturn's problem was actually set in 1855 and was to be submitted by 1857. This was a biennial competition. This was a scary problem because it had defeated everyone who attempted it,
including the great Pierre Simon Laplace. So they were doing this in hope, not expecting anything. The questions they asked were, under what conditions, if any, would the rings be stable if they were one solid, fluid, or made of many separate pieces of matter? And they wanted a full mathematical account. James took on the solid hypothesis first. Laplace said that this was impossible but couldn't prove it. James took it from here. He started at the center of Saturn, forming the equations of motion in terms of the gravitational potential at the point due to this ring. In amazing mathematical method that has never been seen used in that way before, he showed that a solid ring couldn't be stable, except for one instant if 80% of the mass was concentrated in one point of the circumference and the rest was distributed equally. But telescopes didn't show a lopsided structure of that extent.
Sorry for interrupting the story, but this is our new series, The Penny University with Mr. Goddel. So this is a democratic place where we discuss all ideas, scientific, technological, mathematical, and even arts. So if you have any ideas, go in the comments and let's have a discussion. 17th century stuff.
So could a fluid ring be stable? This depended on how internal wave motion behaved. How would these rings stabilize themselves or grow bigger and bigger until the fluid broke up? James Clerk Maxwell used the methods of Fourier to analyze different types of waves that could occur and showed that fluid rings would inevitably break up and separate into blobs. By elimination, he had shown that even though the rings appeared continuous, they were actually separate bodies orbiting independently. More work was to be done though. The examiners wanted a mathematical analysis, but an analysis of the motion of an indeterminately large number of different sized objects was clearly impossible. But per physics, we give exceptions. To get an idea, he took a special case of one ring of equal spaced particles. They showed that such a ring would vibrate in 4 different ways, and if its average density was low enough compared to that of Saturn, the system would be stable. When he took 2 such rings, one inside the other, some arrangements were stable and some were not. And for his work, James Clerk Maxwell was awarded the Adams Prize. He was even the only person to submit, since this was such a scary problem. Even Sir George Airy said James's essay was one of the most remarkable applications of mathematics into physics. This was beautiful and creative, and no one has ever pushed this advancement into this problem such as he did up until we saw amazing discoveries from space probe like Pioneer 11, Voyager 1 and Voyager 2, giving us a close look at Saturn's rings, revealing these intricate structures and diverse components from icy particles to moonlet. The Cassini-Huygens mission provided great insight. For 13 years, Cassini orbited Saturn and capturing breathtaking images and data about the ring's composition, dynamics, and origin. In 1977, the brilliant James L. Elliott led a team of scientists that included Edward W. Denham and Jessica Ming. They wanted to study Uranus using stellar occultation, where you observe a distant star as it passes behind the planet. This journey started right here at the Kidd Peak National Observatory in Arizona. They had the most powerful telescopes to observe the planet. Stellar occultations involved looking at a star passing behind Uranus and measuring the brightness and time it disappeared and reappeared. Then they could deduce information about Uranus's atmosphere, and in March 10th, 1977, James Elliott positioned the telescopes in the path of Uranus's shadow as it moved across a distant star. This was not in the planet itself, but the shadow. The star's brightness didn't just fade away and come back, but it was blinking multiple times. This suggested that Uranus had rings similar to those of Saturn. This was a groundbreaking discovery, and now everyone was wondering about Jupiter and Neptune. What if they also had rings? And by March 4th, 1979, Voyager 1 captured Jupiter's rings, a faint haze ring made of tiny dark particles and remnant of shattered moons and material from the planet. January 1986, Voyager proved James Elliott correct, and in August 1989, it captured a set of rings in Neptune. Recently, we are using more powerful telescopes that we have, and we've been using stellar occultations that James Elliott and his team use to find exoring, the most prominent one being Super Saturn, and finding more than 12 out of 30 exoplanets we've examined to have these planetary rings.
We've also been using it in our own solar system to find smaller bodies that have rings. And currently we've found multiple small bodies in our own solar system that has rings. And all this has given us a new understanding about the origin and evolution of our own solar system.